Hello dear students, in today's class we will try to understand what is called as the magnetic mirroring. So the idea is, so in our earlier classes we have derived expressions for the gradient drift, expressions for the curvature drift, and then we learned how to combine these two for what is called as the total drift velocity or the total or the vacuum drifts, right. So, in today's class we will try to understand how a particle, a charged particle can be trapped within a magnetic field. What kind of magnetic field can result in trapping charged particles? So, the basic idea is the magnetic field has an ability to keep, let us say, the magnetic moment as conserved. So, that means the magnetic moment. So, we have seen that the particle gyrating around a center with a, let us say, gyration radius RL will constitute a tiny magnetic dipole whose magnetic dipole moment is equal to the current times the area. Now, we have seen that, we have derived that this magnetic moment is equals to mv square by 2b. So, now a very important point to consider is that when you make the magnetic field inhomogeneous, we have taken a small approximation saying that the magnetic field of course is changing with respect to space. It is changing with respect to, in our earlier cases, the magnetic field was changing across the y direction. That means the magnetic dou b by dou y is not equals to 0, right, fine. But what we have done is that the magnetic field can change, but the length scale over which the magnetic field changes is sufficiently large than the radius of gyration, one individual gyration orbit. So, let us say if the particle is gyrating like this, we say that as long as within this distance, let us say within this distance the magnetic field is assumed to be uniform. So, we are not going to complicate one single orbit of the particle, rather when the particle moves across the magnetic field, we may expect something like this to happen because of the strength in the magnetic field changing, right. But we will not expect the particle's orbit, one single orbit, to be complicated because the magnetic field strength is changing. So, we know that the radius of gyration is mv by qb. So, in the field alignments that we have taken the magnetic field to be low at a particular point where the radius of gyration will be larger because of the magnetic field, but not due to the particle's mass, right. So, the idea is now we will try to understand how magnetic field can be trapped by constituting a certain type of magnetic field, which obviously changes with respect to space. So far we have not included any discussion about magnetic field being non-static, right. So, now if the magnetic moment needs to be conserved, then we will obviously, if we change the magnetic field, the magnetic moment, let us say if you increase the magnetic field, the magnetic moment will decrease. But if you want the same magnetic moment to be retained, or if you want this magnetic moment to be conserved, even though the magnetic field is changing, the only other parameter that you can tweak is the V perpendicular. So, if you increase the magnetic field, the magnetic moment will try to decrease, but at the same time if the perpendicular component of velocity is increasing, then the magnetic moment will remain a constant, right. Now, the velocity is always a combination of the perpendicular component plus the parallel component. Now, if you are changing the magnetic field, the V perpendicular is of course compensating the change in the magnetic field so as to keep the magnetic moment conserved, but the V perpendicular changing should also influence the V parallel, right. So, if the V perpendicular is increasing, the V parallel should decrease so as to keep the V constant, right. So, this is a special type of conservation. I mean, this is conservation under a special case, let us say. So, what type of conservation is this? So, generally we are very well aware of the conservation of, let us say, conservation of mass, conservation of charge, or conservation of energy. So, while discussing the charge conservation or mass conservation, we do not impose any conditions. We do not impose under this conditions only the mass has to be conserved. Mass is constant always, irrespective of any process. In the beginning and in end, mass is conserved. Energy is also conserved like that, right? So what it means is that this is a universal conservation. That means under any given circumstances, as far as you are not taking away anything, the mass, energy, charge, these quantities are always conserved. But the magnetic moment conservation is not like that. So in plasma, what we do is magnetic moment is conserved only if the magnetic field is not changing much within one gyro orbit. So that is the basic condition that you put that you put on the magnetic moments conservation. So this type of conservation, which is not valid throughout, but rather valid over a certain limit of, let's say, variable change, is generally called as the adiabatic invariance. Adiabatic invariance. Right. So let's see what else we learn about adiabatic invariance. So we will try to use the variation or the conservation of magnetic field, magnetic adiabatic invariance of. So essentially, the adiabatic invariance of the magnetic moment is what leads to the magnetic mirroring or particle trapping. Now, why are we discussing the magnetic mirroring or magnetic particle trapping in atmospheric or space physics? Is that we will always see that if you have the magnetic field line like this, let us say, for the case of Earth. So, this is the side that is facing the sun, right? The magnetic field lines are diverging away from the geographic south pole and converging at the geographic north pole, right. Now, what we will see is that the magnetic field lines always accompany, or let us say facilitate, the gyration of charged particles to be travelling from one pole to the other pole. That means there are charged particles which are moving from one point to its conjugate point. So this kind of so this particle is trapped. So this will keep gyrating from here to here like this. So it will keep gyrating depending on the charge. It will keep gyrating from one point to other point. So what is this alignment of magnetic field? What is the nature of this magnetic field, which actually facilitates this kind of this kind of charged particle trapping is of interest. So that's why we are studying the magnetic mirroring idea, and we will try to see mathematically what kind of magnetic field will allow such a particle to be trapped. So that's the basic idea, right? Now let's say for this problem we'll consider a field type of field. Let's say we'll consider a certain geometry of the magnetic field, because eventually we are now speaking of the inhomogeneous magnetic field. So there should be magnetic field which is changing with respect to space, and this inhomogeneity should only be at any given point. If the particle is gyrating, the magnetic field should not change much within the particle's orbit radius, but over large distances the magnetic field is of course changing, right. Now let's say, so the geometry is cylindrical again. So we take a cylindrical geometry like this. So the coordinates are, this is the r coordinate and this is the positive z, and the anti-clockwise direction or is the phi direction, right. Now the magnetic field is chosen like this. Let's say the magnetic field lines are trying to converge right. Now what is the direction? So this is the z direction. So the magnetic field is now pointed in this direction. The original magnetic field is pointed in the z direction. Okay. Now what is the phi direction? So this is the r direction. So magnetic field has the z component, right. Now we take that the magnetic field's phi component is 0, and we will also assume that the magnetic field is axis symmetric, which means that the magnetic field at for a given value of phi, for a given value of r, any value of phi, the magnetic field will be constant. Will be constant. So, if you take here any point, if you take, let us say at a distance r, for any value of phi, the magnetic field is same. That means that the magnetic field is symmetric about the axis, right. Now, the most important thing about this type of field alignment is that the magnetic field is, of course, is pointed in the z direction, but we are not saying that the magnetic field has an r component. So, what is the value of Br? What is the possibility of having a Br? Let us say. So, let us say the magnetic field is kind of weak here, and the magnetic field is, let us say, is strong here, and the magnetic field is weak here. What does it mean? So, there are less number of magnetic field lines per unit area in this region, right. The magnetic field lines per unit area in this region are less, and more number of field lines per unit area here. So, let us say if you take any distance r, the magnetic field strength at this point will be something. If you take the magnetic field at the same distance r, the magnetic field strength will be different. So, that means that the magnetic field is changing with respect to r. So, there is invariably a magnetic fields component across the r direction, right. Now, how do we find that component of the magnetic field across the r direction, right. So, if you observe carefully, so the idea is simple. So, in earlier cases we had just to remind, the magnetic field pointed in the z cap direction and the gradient of the magnetic field pointing in the y cap direction. So, which means that the magnetic field is perpendicular to the gradient. So, while we were discussing the gradient and the curvature drifts, right. But here in this case, the magnetic field is pointed in the z cap direction and the gradient of the magnetic field. So, here the gradient of the magnetic field. So, what is the direction of gradient? Of course, this is the direction of gradient. The gradient is the change in the maximum change in a particular physical quantity. The direction of this gradient is obviously in the z cap direction itself. So, magnetic field is changing, is increasing in this direction, right. So, the magnetic field's gradient is also in the z cap direction. What it means is that now we have a scenario in which B is parallel to del B. Okay. So, the magnetic field is parallel to del B. So, this is a more realistic magnetic field. So, if you consider the magnetic, so let us say this is the pole, this is the equator, let us say this is the equator where the magnetic field lines are placed farther apart, and when they approach the pole, the magnetic field lines will try to converge, right. So, this is the equator and this is the, let us say this is the pole, a more realistic magnetic field. Now, let us try to understand how this kind of configuration, if you have to conserve the magnetic moment, how this kind of configuration will result in the trapping of a particle. So, what do you mean by trapping? The particle should always travel between two poles of the magnetic field. That's what the mirroring is. So, there should be some physical effects due to which the particle should change its trajectory and get reflected from a particular point, right. Now, let us see. So, now where do we start? We start from the simple idea. We will write the magnetic field as B is Br across r cap plus B phi across phi cap plus Bz across z cap. Now, B phi is 0. So, we will simply write the magnetic field as Br r cap plus Bz z cap, right. Now, how do we find Br? We know Bz, we know that Bz is the non-zero component of magnetic field, whose gradient is also present, right. So, Bz is of course non-zero, B del B is also non-zero. But how do we find Br? Simple, we will say that the magnetic field, the gradient, the dot product should be 0. Okay. So, how do we write it? We write it as 1 by R dou by dou R of R Br plus 1 by R dou B phi by dou phi plus dou Bz by dou Z is equal to 0. This is anyway 0 due to the assumptions itself. So, we write 1 by R dou by dou R of R Br plus dou Bz by dou Z is equal to 0. So, R Br is minus integral 0 to R dou Bz by dou Z into dr. Br is equal to minus R square by 2 times dou Bz by dou Z, or which implies that Br should be minus R by 2 times dou Bz by dou Z. Now, one very simple thing that we can understand from here is that Br arises only due to the fact that Bz changes with respect to Z. If there is no change of Bz, the Z component of velocity with the Z direction, there is no possibility that we can get Br. It is very simple. And how does Br change? Br changes linearly with respect to R this time, right. So, let us say now this is the third time that we are dealing with the magnetic field and charged particle. So, in every case we always say that the magnetic force, the force that is experienced by the particle is always simply Q times V cross B. So, the differential equation is m dV by dt is Q times V cross B. So, any type of magnetic, so if the magnetic field is changing with respect to space, so in the second case, in the first case we solved this equation directly, we got the solution as well, which indicated that the particle's velocity components will add in such a way to give a circular motion, and the Vz component will allow the particle to be travelling parallel to the magnetic field. In the second case, we took this magnetic field and we made a Taylor expansion such that B0 is the magnetic field at the center of the gyration orbit, and B0 remains B0 within the distance of RL, right. Then in the third case, this case, what we are going to do is we are still going to do the same thing. Br is minus R by 2 dou Bz by dou Z. So, in continuation, so m dV by dt is simply Q times V cross B. So, in the cylindrical coordinates Q times V phi Bz minus Vz B phi Q times Vr Bz plus Vz Br, and Fz is equals to Q times Vr B phi minus V phi Br. Right. So, these are just the components of the Q times V cross B. So, we always had this type of curl products. This only gave us the idea of how the velocity changes with respect to the time in the presence of a certain type of magnetic field. Right. Since B phi is 0, we immediately get rid of this term 0 and this term. Right. So, we have term number 1, we say 2, we say 3 and we say 4. Right. Now, so if you look back, these three terms, let us say term number this, if you let us say take this to be equation 1, this to be equation 2 and this to be equation 3. If you look back, term number 1 and 2, of course, they were similar. So, we had f x being given as, let us say, q times v y b, and f y is minus q times v x b, and f z was of course 0. When was this? This was when the magnetic field was not changing with respect to space, a homogeneous magnetic field. Then we said that there is no force that is acting on the particle in the parallel direction. So, V parallel is uninfluenced, V perpendicular is what influenced. So, V perpendicular was Vx and Vy. These two components of velocity were influenced by the magnetic field, and this component V parallel was not influenced by the magnetic field at all. Right. So, this is very simple. I mean, if the magnetic field's vector is parallel to the velocity, then the curl becomes 0. So, there is no point of discussing about it, right. But when it is not that, okay. So, then we combined these two differential equations, then we said that the velocity will be such that it is executing a simple harmonic motion around an imaginary guiding center, right. But here what you see, the magnetic field is along the z direction, and the velocity component, and since the magnetic field is being across the z direction also, there is still a force Fz which is non-zero, of course. And so, Fr and F theta, so terms 1 and 2 will give us the circular motion. So, it is simply the Larmor's precision that we have seen in so many cases. So, terms 1 and 2 will give us the circular motion. Now, most importantly, this is the force that is acting in the parallel direction is something new for us. So, let us see how this non-zero force across the z direction will give us some physical effects, right. So, let us say Fz, like we have calculated Fz, Fz is minus q times V phi Br, right. So, we know that Br was calculated to be minus 1 by 2 R dou Bz by dou z, right. So, if you substitute this, and since there is a charge term which can take positive or negative, we can write Fz is equals to minus plus q V phi R by 2 times dou Bz by dou z, right. So, we say that R is equals to RL, and V phi can be plus minus V perpendicular. Why is it so? Because our geometry was like this. So, this is the z direction, and any revolution, this is the phi direction, and this is the r, right. So, velocity component which is across z direction, is simply the parallel direction, and velocity component across the phi direction, which is z is perpendicular to phi. So, velocity component across phi direction is simply V perpendicular, right. So, this is the Fz. So, the force which of course, the force is clearly due to the magnetic field, nothing else. So, the velocity component being perpendicular to the magnetic field Bz, Fz is the force that is resulting from this configuration, right. So, we can write Fz as qv. So, now Fz is minus plus q v perpendicular r L divided by 2 times dou b z by dou z, right. So, what is the effect of this particular force? You know, what we have done is we have taken a particular type of field configuration. We have taken a particular type of field configuration in a cylindrical geometry. Then we have said that there is a gradient of the magnetic field which is parallel to the magnetic field itself, and then if a charged particle starts to experience this type of magnetic field, we will try to understand what will be the effect. So, first result is that the magnetic field imposes a force Fz which is non-zero this time, and if this force is non-zero this time, so what is the effect of this particular force, right. Now, let us substitute this force Fz and try to see the differential equation that results. So, Fz is dVz by dt is simply minus plus q by m v perpendicular RL by 2 times dou Bz by dou z, right, or we will write m Vz dVz by dt as minus plus Vz q v perpendicular RL by 2 dou Bz by dou z. We know that RL is m v perpendicular by qb. So, m Vz dVz by dt is minus plus Vz q v perpendicular by 2 m v perpendicular divided by q Bz times dou Bz by dou z, or d by dt of half m Vz square is minus plus m v perpendicular square divided by 2 Bz into dou Bz by dou z into dou z by dou t or dz by dt. Say that d by dt of half Vz is parallel, v parallel square is equals to minus plus m v perpendicular square divided by 2 is w perpendicular divided by Bz times dou Bz by dou t. Right. So, this is the consequence. The consequence is such that, so we have calculated Fz. Fz is nothing but m dVz by dt, and with Fz we have made some simplification. So, we have written Vz as the parallel component and dou Bz by dou t. So, now see the point is that the rate of change of the parallel kinetic energy depends on the perpendicular kinetic energy, of course, and the change of the magnetic field with respect to time, right. So, we will stop here. We will try to see how this conservation of energy or leads to the conservation of the magnetic moment, which we call as the adiabatic invariant, right, and eventually all these things leading to the trapping of charged particle in a magnetic field. Okay, so we will stop here. We will continue this discussion in the next class.